So for our second video on inverses, we're going to actually focus on how to find the inverse of a function. First step we want to do is figure out if the inverse function actually exists. Is it one to one? If it is, then we're going to go through the process of switching x and y or whatever variable we're looking at, really switching the inputs and the outputs. That's what an inverse is going to do. If it is an analytical problem, so something where we have an equation, we're going to resolve that equation for the new y, which was the old x, and then write it as a function, an inverse function notation. But first, let's start with graphs. And for graphs, what we are effectively doing is when we take these um, lines and find the inverse, we're taking points on that line and reflecting it over the line y equals x. So we're switching out the x's and the y's, which is reflecting it over this dotted line that I've added in. So we're going to find a couple points. So I'm going to pick a point here at like 0, 2. And I'm going to graph the inverse of that, which would switch those uh, values around. And now I've got a point at 2 comma 0. I'm going to continue to do that with a selection of points. I'm going to go here at negative 2, 1, 2, 1, and my new point is going to be at 1, negative 2. I'm starting to get an idea of what this graph is going to do. I'm going to pick another point here at an interesting point, 4, comma 4. And what's interesting about that is when I graph the inverse of it, actually is that point again. Let's grab one more point. I think we should have enough to make a decent approximation of this line. Pick this point here at negative 4, 0, which would then put me at 0, negative 4. Again, switching the x and the y around. So now I think I've got enough to show the equation or the graph of this inverse function right there. So again, we're taking this blue line reflecting over the line y equals x by taking our points and switching the x's and the y's. And it works for all sorts of different graphs. We look at the second graph right here. This is what is called a logarithmic function, which we're going to look at in the next series of videos. So I can do the same thing. I can take a point here at 1, comma 0 and switch it around to 0, comma 1. I can pick another point. I'm going to have to cheat a little bit on this one because our values are not going to be really nice. But I'm going to call this one 3, 1 a point, even though it's not quite there, but it's pretty darn close. I'm going to call it 1, 3. And I'm going to cheat again a little bit with a point down here. And I know it doesn't actually hit this value, but I'm going to say that it's really darn close to 0, negative 4. And so it's going to be pretty close to negative 4, comma 0. So again, I'm getting this shape of the graph. It looks kind of curvy. Looks like it's going to do something like that. And so that's, again, the inverse. And believe it or not, that's our exponential function. And the inverse of that is a logarithmic function. Interesting. So that's what we're going to do with graphs. We're going to take ordered pairs, switch the coordinates around, and regraph it based on that. And it should always reflect over the line y equals x. So what about tables? Same thing. We're going to take all of our inputs, which are our x's, those now become outputs, and our outputs become our inputs. But again, before we do this, we want to check first to make sure it's a function and is one to one. So I'm checking here all my inputs. I see no repeats, so it's definitely a function. I look at my outputs here, no repeats there. It's definitely one to one. So there is an inverse. My inverse is going to be 0, negative 2, negative 1, 3, and I'm switching the inputs and outputs. 5, 4 becomes 4, 5. 7, 9 becomes 9, 7. Negative 3 becomes 8. And then 2 and 9. In our next relation, it looks again like it's a function. All my x's are all good to go, no repeats. But I have a problem here with my y's in that I do have a repeat. So this is not going to have an inverse. It's not one to one. So I always want to check that first just to be sure. Because if it's not one to one, there's no point in finding the inverse. It doesn't exist. And so what about equations? Equations can get a little bit tricky. I'm going to start with number 2 because I think that one's going to be easier to see what's going on. I've got f of x equals 2x minus 3. I'm going to rewrite that as y equals 2x minus 3. All I've changed is I've called f of x y. They're still representing the same thing. So here's the magic. I'm going to take my x's and y's and I'm going to swap them out. X equals 2y minus 3. Now, to find the inverse, I'm going to take that new equation that I have and resolve it for y. So I'm going to add 3 to both sides, and then I'm going to divide by 2. So I'm going to have y equals x plus 3 over 2. Because I'm actually want to write this as an inverse, I'm going to write it as f inverse of x equals x plus 3 all over 2. Interestingly enough, if I take this function and I plug it back in for x, composing a function and its inverse, I always get x for my output. Always works out that way. So what about a question like number 4? We have g of x equals the cube root of x minus 4. I'm going to do the same thing. I'm going to take my function and rewrite it as y equals the cube root of x minus 4. And then I'm trying to rearrange it after I've switched my variables. So now y becomes x and x becomes y. So I resolve. I'm going to add 4 to both sides. And then cube both sides. So I'm going to have y equals x plus 4 to the third power. Oh, hold on. I have to write that as an inverse. F inverse of x is x plus 4 to the third power.